So we had a review week, and then we had the exam. Now it's time to go back to learning new stuff. Okay. So where do I want to start? I want to talk about many-body wave function, or yeah. So we already have seen some extensions of one-dimensional Schrödinger's equation, right? What we did is, in one dimension, we had psi of xt, and we just expanded it to 3 dimensions by simply writing psi x, y, z of t, right? So what if you have many particles, more than one particle, okay? What do you do then? Here's what you do. Let's say you have 2 electrons. No, let me start with 1 electron. 1 electron in 3D has psi x, y, z, t, right? 2 electrons in 3D Can you guess how you would extend it? X1, X2, Y1, Y2. Very good, very good. That's the right way to go. So you might think that somehow there are 2 wave functions. You might think. That's the orbital view. So let me just write it down like this. You might think that there are 2 orbitals okay. This is how, let me say, chemists would see it. But a quantum chemist, so it's not about being chemist or not, would see it as you said. Like, she would be careful to say that, okay, this view, this orbital view, it's very useful, and we will see it make a great comeback after the density functional theory. But the right way to see this is x1, y1, z1, x2, y2, z2. That's the right way to go. This is the many-body wave function. Many-body wave function. There is t, sorry. Okay? So what? Right? So what? What is the difference? It seems like there is no difference at all. So let's look at N2 molecule. Okay, it's 14 electrons. And I'm ignoring right now, the nucleus. Okay? So I have 14 electrons. In the orbital view, I have 14 orbitals. Phi 1 of x, y, z Let me not write t anymore, just because that's not the point, and up to 514 x, y, z. Okay? Let's see how much of a disk space I need if I want to put it in a computer. Okay? How much of a disk space? What do I mean by disk space? So I mean that just like we did with the hydrogen atom code, I'm taking a grid in each direction, and the values in that grid would represent the orbital, okay? Just like we had here. So we had, where is it? Do we have F here? Yeah, F is here, and we can see it. So F is a 4-dimensional matrix. Let me show you size of F. So it's 50 by 50 by 50 by 14. Okay, so 14 orbitals, and each one is divided in 50 grids. So how much does this make? That if it was 100, it would be 100 cubed, right, times 14. So 14 million, right? Can we call it 14 megabytes? Is it okay? So this one has 14 megabytes of storage. Now let's move to many-body wave function view. Many-body wave function view. Now this beast is composed of x1, y1, z1, dot, 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 up until x14, y14, z14. So it's a tensor of 100 by 100 by 100 by 100 by 100 by 100 up until how many coordinates you have here? 42, right? So it's we need how much space? We need 100 to the power of 42. Okay, 10 to the 84. So it doesn't fit in the universe. If the universe was a computer, because universe has and this is atoms in the universe, observable universe. Then you might ask, where is that wave function stored? I have no answer to that. But and you know, 100 was an arbitrary choice. In principle, even one-dimensional wave function is infinite dimensional, right? You remember Hilbert space? Now multiply that Hilbert space. Every time you have a particle, you get another Hilbert space. So, okay. So besides philosophical questions where the wave function lives, okay, how on earth are we going to calculate it? How are we going to have any calculations with it? Okay, because 2 electrons is 6 coordinates, 3 electrons, 9 coordinates, okay? So there's a problem, and we will come back to this problem soon. But before we come back to this problem, I need to talk to you about spin. And to talk about spin, I need to talk about this experiment that I usually never talk about, but it's a very bad idea to not talk about it, because usually serious quantum mechanics courses actually start with this experiment, okay? So, Stern-Gerlach experiment. Have you heard of this? No? You said something? So let me give you a little bit of a background and take my knowledge in here like 80% trustworthy, okay? I sometimes mix up which one came first, which one came later. But this is a very early on experiment, 1921. This is before Schrödinger's equation. This is back in the days and before matter wave idea, right? Back in the days when it was Bohr, main actor was Bohr, and his idea was that angular momentum is quantized. Do you remember this stuff? Angular momentum being quantized. So, what was angular momentum? Angular momentum is actually about something being rotating. Like, so for example, in Bohr's case, he was thinking about electron going in an orbit. Okay? When you rotate, you have some angular momentum. If you remember, we would say that mvr equals to n times h bar. Do you remember this? That was Bohr's postulate. So Bohr also realized that there is another implication of this. The implication is that this is a charged particle rotating. So there is a current, right? And current, when you have a current that rotates, you get a magnetic dipole moment. Do you remember this stuff? Yes? So there is magnetic dipole moment, which is current times the area. And the area has a vector here because depending, if you rotate like this, then the vector points outwards like that. Do you remember those stuff from Physics 102? Yes?
Isn't it the electrical field, mu, or magnetic?
This is magnetic dipole moment. And yeah, so it would interact with magnetic field. It would create its own magnetic field, and it would interact with applied magnetic field. And what would happen is that it would align with magnetic field. So if magnetic field is in this direction, then the magnetic dipole moment would align with this. Okay? So the electron, since it's negative charge, it would be actually rotating backwards. So not this way, but that way. The electron would rotate around magnetic field like this. But this is just precession. Precession means not moving like this, but turning. Okay? So, electron would arrange its own orbital so that it fits, it aligns with magnetic field. So far, so good? But Bohr at the same time is telling us that it should be quantized, right? So these people, instead of electron, I guess electron is hard to work with because of its charge. So they take silver atoms. Can you check? I think it has 47 electrons. Is it the case? Did you check? 47 electrons. And I think it ends with 4s1. Can you also check that one? Okay. So it has a closed shell, more or less closed shell, and one electron hanging out. We can think of it that way, and this is a modern picture. 5s1? Are you perfectly sure?
Double check the copper is 4s1, I think. The silver is the next row.
Okay, just check it. 5s1. Okay. Now, for example, what do we not know back in the day? Okay, back in that day, we don't know about electron spin. And that's the whole point of introducing Stern-Gerlach. But interestingly, counterintuitively, in the day of Stern-Gerlach, electron spin was not there. Okay, the idea was that the electrons of silver would have quantized angular momentum and would have concomitantly, let me use that word that I use in papers, concomitantly it would have a discrete magnetic dipole moment. Okay, now what Stern-Gerlach does, it says, okay, if I want to, if I apply magnetic field, then it would just flip the spin. No, not the spin. There's no spin. Angular momentum. Flip the angular momentum. Okay, magnetic dipole moment. But they want to move it. They want to move the ions, the atoms. Okay. So they instead use a magnetic field with a gradient. Okay, magnetic field with a gradient. So it's like a magnetic field, but it has a gradient. So you can think of it like this. Okay, does it make sense? So I'm not sure which way the atom would go depending on this magnetic field, but the point is, depending on the gradient, so you enter with angular momentum pointing up, let's say, you go up. Okay? You enter with angular momentum down, you go down. That's the whole point. Okay? So, what is expected from classical theory? What is expected from classical theory is that you shoot atoms, right? They can have any direction in angular momentum. Nothing is directing them, right? So they could go up a little bit, up a lot, or down a little bit, down a lot. So classically, you expect the atom goes disperse continuously here. So far, does it make sense? Yes? That's the classical expectation. What is the reality? Well, the reality is that they go over here, or they go over here. So just as it was, I wouldn't say that Bohr would expect it. Bohr actually was confused with this result, okay? But just as it was in the air, the subject was that the angular momentum is quantized, and this experiment shows some quantization. Do you remember this experiment? Yes? Is there a third line in the middle?
Actually, the north pole of magnet is above and the south pole is down, and the electrons passing through in between, and there's a screen there, and some of the electrons go up and some of them.
So there are only two lines,
Yes.
right? So it's actually measurement, right? So let's say the magnet is like this, and then there is a measuring screen. So some of the atoms go up, some of the atoms go down, and there are just two lines. Just like when you do this genetics thing, you have these lines, just like that. You would expect a continuous thing, but you get lines. Very good. So, fast forward, I think 4 years later, this experiment was explained by electron spin, okay? Saying that it's not about angular momentum of the electron in that orbital, but it is due to intrinsic property of electron called spin. Are you with me? Yes? So, let me talk about spin. So, electron spin is either plus 1/2 or minus 1/2. Okay? And the modern explanation is that outer shell electron has this room for it, and it's alone there, like upspin, right? Or it can be downspin. It can be alone and it can be downspin, living there. So upspins go up, downspins go down. Because just like angular momentum, the electron spin results in magnetic moment. Okay? Because of that magnetic moment, they interact with non-uniform magnetic field. So non-uniform magnetic field would shift up spins up, down spins down. So far, it's quite weird, right? Same. No. You can think about it like that, but we definitely know that it isn't the case. Okay? Why? Why? Because our theory, our current modern theory, tells us that electron is a point particle. Okay? A point particle cannot create, first of all, you cannot rotate a point, right? Second of all, even if you can, there is nothing that goes around. If you rotate a point, it's just a point. So even though you have a charge there, rotating that charge wouldn't create a magnetic moment. So it's an intrinsic property, like a label on top of an electron. Or to confuse even much further, it's an extra dimension for electron. So besides, we will actually write it down in the wave function soon. Besides x, y, z, there's also the spin dimension of the electron, up, down. Okay?
It's not related to the rotation movement. It's another, dimension of electron.
Exactly. And it turns out that for electrons, the spin is 1/2 or -1/2. For photons, for example, do you remember what is the spin for photons? Is it 0? Is it 1? Okay, can you check it? Well, very good questions. All these make sense once you start thinking about relativity. So relativistic Schrödinger equation, like putting together also relativity into it, and trying to explain these Stern-Gerlach experiments. By the way, the point of Stern-Gerlach is not made yet. If this is weird, there's much more weirdness coming your way. So brace for it. What is the spin of photon? 1. So, do you know anything that has 0 spin? No. So, for example, neutron, I think, if I remember, also has +1 or -1/2. And by the way, this is spin 1 means that it can be -1, 0, and 1. Right? Very good. They don't calculate this. They just like the wave function. Very good question, by the way. Okay, we constructed a theory, Schrödinger's equation, based on our observations, right? And there is this actor there, which is the wave function. And our current interpretation, modern interpretation, tells us that that forms the reality itself, but the reality is detached from our measurements, right? So it's a theory, it works, it's a mathematical construction beyond our reach. Similarly, spin is a mathematical construction, but everything is mathematical construction, and like you write down the law of gravity, okay? So you are not asking whether it's real or not, you are asking how people came up with it, right? So people came up with it by looking at the experiments. The only way, so they realized that the only way to explain, let's say, Stern-Gerlach experiment and other stuff, some atomic physics. For example, you apply magnetic field, okay? Actually, this is a way simpler explanation than anything else. You apply magnetic field and you see splitting in the energy levels, right? So why is that happening? Because they realized that besides n, l, and m, the quantum numbers that we have in the Schrödinger's equation, we need another quantum number, mz, that would correspond to upspin and downspin. Does it make sense? Yes? So it's
number was suggested by the experiment.
yeah. This, like the idea of spin was suggested to explain the experiments. Okay? But once it was suggested, so the thing is that that's why it's a good idea when you get older, maybe, to go back and sort out the history of science. Okay? Like, for example, some of you are working with DNA, right? And it's a double helix. But, for example, the two Nobel Prized Wolfgang Pauli had an idea of triple helix, I think, for a moment, for a while. Okay? Like, after it's done, we just take it as granted, as scripture, like coming from God, and this is sacred. But it came there with a process, with a scientific process, which is you put out falsifiable theories, and unless they are falsified, they are the modern theory. So we have a theory of electron spin that came up to today and went over all the hurdles, but it can still be improved based on some new experiments. Does it make sense? But right now it fits with everything. Its name is spin. It doesn't spin. So experimental observation of electron spin, which is not spinning, just that property, apply magnetic field and it splits into two pieces. Make sense? Yeah. Does it have a spin? Can you check? Is it 1/2 spin, neutron?
It's fermion, so it should be 1/2.
Yes. Can you still check it? So that's another thing. By the way, neutron is a different story. Neutron is not fundamental particle. Okay? It's composed of quarks.
Yes.
And its spin, I'm right now talking about something that's out of my knowledge boundary now. Its spin, I presume, comes from some arrangement of spins of quarks. Does it make sense? Okay.
At that time, they thought the electron is spinning, and they called that.
No.
Dimension is spinning.
Okay. So the people who came up with spin, I don't remember their nationality, but maybe, let's say, if they were German, which they are not, I guess, maybe in German it's something else. Like spin, I agree that it's confusing to call it spin, because then your mind goes to something that spins, which is partly true. It is as if something spins and creates that magnetic dipole moment, but it isn't. There are seriously weird stuff here. If you rotate, okay, now you will tell me that you can't rotate an electron. But if you rotate an electron 360 degrees, it doesn't come back to itself. Its up spin becomes down. Never mind. Never mind. The idea is that they are living in a different symmetry spaces. Spin and space have different symmetry spaces. One is SO3, the other one is SU2. If you are interested, I can send you a video about it. All right, moving on. So what was so weird about Stern-Gerlach experiment? Okay, this is before Schrödinger's equation. And I think this motivated really the interpretation of quantum mechanics. Here's the thing. You basically send a spin, you basically send the atom. Let's now stop talking about the atom. Let's send the electron, okay, into an apparatus that has a magnetic field in z direction. Okay? By the way, the other interesting weird thing is that when the apparatus is in z direction, they get separated in z direction. That's already weird. Okay? So your measurement is affecting the state of the system. Because, look, classically it could point in any direction that you want, right? The magnetic moment. But quantum mechanically, what comes out is upspin in z direction and downspin in z direction. So what comes out in the experiment is in z direction there's a line here and there's a line here. So far so good? Then we pass this through. For example, we measure z again. Okay? What is the outcome? So this was 50%, 50%. Once you did the measurement, it's upspin, so it's 100% upspin in z direction. Okay, 0% down. Downspin is 0%. So far so good? Do you have any questions?
So we can separate the, for example, plus 1 over 2 and minus 1 over 2 spins and keep them just like that?
Yes.
Forever?
Yes, in principle, yes. But this is, so in this case, the weird part is this part, right? It shouldn't have had two lines, it should be a continuum, right? And we just got this, right? So it's already weird. But the weirdness continues. So let's now take this portion, duplicate. Once you pass through upspin, you are 100% upspin, and this part of the experiment shows it, right? Let me just use this thing. So this part of the experiment tells us that once you go over this part, once you choose this part that is upspin, it comes out as upspin over here as well, right? So what do you classically expect? You have an upspin coming, and now let's calculate in x direction. So you are facing something that's coming towards you, and it's facing z direction, but you are calculating in x direction. What do you expect? 0. You expect 0, right? Classically. Can you tell me what happens? Huh?
Again, we have a spin. 50-50.
50-50. 50-50%. So we get 50% of x from here, 50% of x down here. Okay? And no 0. Do you understand it? Yes, tell me.
Yeah. So in the beginning, it could have any of the magnetic moment, but when you
Classically.
classically, it could have, for example, it could have an upspin, downspin entirely. It's just random,
Hmm?
and when you pass, after it's 50%, like the first, it could have had any moment, but it chose to have all upwards. But then while you pass, and it splits into 100% upwards rather than just
Yeah. So I'm not sure whether you are asking it as a classical physicist or quantum physicist. But to get rid of the confusions, let me tell you what the quantum version of it right now, okay? The quantum version tells you that measurement of spin in z direction, let's have an operator sigma z, okay? Sigma z is an operator and it has two eigenvalues and two eigenvectors. The eigenvectors are up in z and down in z, okay? So since these are two eigenvectors, do you remember the energy measurement would create only the energy eigenstates after the measurement? So right now it's a combination. We don't know the combination. A up, B down in Z, right? But once it passes through it, A squared probability will be up, B squared probability will be down. Did you get it? Yes? Now, once it is here, we know that this is the state. 1 times sigma z plus 0 times down z, right? Now, if you do sigma z experiment again, quantum mechanically, since that value is 1, 1 squared is 1, it's 100% upspin. Are you with me? Yes? Now, what happens here is that you have up sigma z, 100%, 1 times sigma z, right? But now you are measuring sigma x, okay? And its eigenvectors are up x and down x, okay? So you need to represent this in terms of up x and down x. And if you do that, you will see that it's up x square root 2, down x square root 2. I think, I hope. Whatever, I'm not sure about this plus or minus. But in any case, their coefficients is 1/2 and 1/2. 50%, 50%. So if you want to construct this up z, you need to use up x and down x in a certain fraction so that you get those outcomes. Are you still with me?
So again, if we measure after sigma x measurement, this sigma z again. From
Good.
both of them,
Yes.
you get 100 again.
No. No. You get 50-50 again. So you started here, you came to z measurement, you went up, and you took this one, you made x measurement, and you took, let's say, this one, you did z measurement, and still you are going to get 50-50. 50%, 50%. So this is, it doesn't make sense classically because, like, let's say something happened here and we weren't sure, okay? But now we are sure it's 100% up in z direction. But then, since we are breaking it down to up x and down x, after z measurement, it's still 50-50 over here as well. So x measurement actually erases the knowledge of z measurement.
But we separate all the parts so they can
Yeah.
arrange their spin again. How can it possible? So, I mean, electrons have the spin, so we separated them to up and down spins, and we measure
In z direction.
in z direction.
Yes.
Measure and separate them in x direction again for up and down spin. And then if we measure the z direction, it's 50-50, but we separated them, hocam.
Exactly. So I like that you see the weirdness. But this is the case.
So they can rearrange themselves somehow.
Exactly. That's the wave function collapse. Okay, so it comes like this to you, and you just measure in this direction, so it just collapses into this one or this one. That's why we have that measurement collapse idea. That's why people start with Gerlach so that you see the weirdness here. Okay, so this knowledge is erased once you measure it in x direction. And it's not, as far as quantum theory goes, it's not about like interaction somehow, like there is a rule there is a physical interaction that bends it like that because we have measured it in that direction. Even if there is, we have no theory for that. So it's a theory of measurement collapse. We don't have a theory for measurement collapse. We just know that after that measurement, the previous knowledge is erased. Okay? Are you still with me? Yes?
It was still 50-50 after the first set, right? Not 100% for the last one.
Yes. It was still 50-50 for here, but once it's going in here, we know that it's 100%. Okay, if you want, we can put another z here, and it's 100% up z, okay? And 0% down. We know that it's up. Over here, we have the knowledge of up z, but we lose that knowledge once we measure x. Okay?
But if we don't measure anything, we will have that knowledge.
Let me try to understand what you are saying.
For example, if we don't measure x or y direction, and if we separate all the up spin electrons, we can put them in a bag, and we know that they have all up spins forever.
I'm totally lost. Start over, please.
Okay, if we measure, for example, z direction, and if we don't measure any other direction, for example, x or y, and we separate, for example, up spin electrons,
Yeah.
keep them in places, we will know that
Yeah.
all of the electrons will have up spin
Yeah.
forever.
Yes. Provided that it's not interacting, it's coherent and whatever. Yes. Okay. So I wasn't expecting this to take this much, but I'm happy that it took this much. So now you see that the weirdness was already there before Schrödinger's equation was there. 5 years earlier, we had this problem. Okay. I was planning to talk about the spin part, but we don't have enough time. If you want to linger on this one, if you have any questions, please ask now. For example, one thing is this. You did Z, right? you took 50%, you did Z, 100% Z up, right? Now, you could do also like 45 degrees in Z direction. Like that's also possible. Like something is coming like this. Instead of doing it 90 degrees, you can do 45 degrees. Then I guess it will be 75% up Z, 25. So you can arrange it actually. But it's always up and down. The separation is always the same. Sure.
Why is that? Like it's 45. Let's think about like coordinates. Why there's no x component or something like or other axis components? It's 45.
Yeah.
So
I don't get the question.
it's not pure one axis, right? If it's 45.
I think I'm trying to remember what was the formula for it. There was a formula for probability of outcome based on the theta. Okay? So when it's perfectly aligned, 100, and if you send up spin, it comes out as up spin. As you move it towards 90 degrees, it will be 50-50. But if you go close, like 45 degrees, I think it will be 75-25.
And only in z axis.
Yes, what is your question, to be precise?
Like when we were talking about axes, we should, when we are going to this like direction, let's say we have one axis, second axis.
Mm-hmm.
When we are going not straight, it's not zero anymore for other axes. Like we have some value from other axes. Like it's not pure z direction anymore.
Yeah.
Is it too classical to think about it like that? Like
Yeah, for sure. You just leave classical ideas behind. Okay, whichever axis you are measuring, that defines your operator, and that operator has two eigenstates. It's up in that direction and down in that direction. So it cannot, if that is the question, it cannot come out up in this direction anymore. Like you can measure it up in this direction, and that will be up in this direction. But it's not that way over here. I hope it made sense.
I will try to read it.
Okay. Take good care.